So a brief introduction to Professor David Kirsh. Dr. David Kirsh, Professor, past chair of the Department of Cognitive Science, UCSD, received a PhD at Oxford University, did his postdoctoral work at MIT, AI Lab, held research or visiting professor positions at MIT and Stanford, and at the Bartlett School of Architecture at the University College London. He has written on situated and embodied cognition, how environments can be shaped to simplify extend cognition, and how space, external representations, our bodies, and even manipulated objects become interactive tools for thought. He is co-director of the Arthur C. Clarke Center for Human Imagination and on the board of directors of the Academy of Neuroscience for Architecture. He is an adjunct professor of Trinity Laban, Conservatoire of Music and Dance. So it's a huge pleasure to have David's presentation here today. I will play his keynote now.
Thank you, Abel. It's a pleasure to speak at Design Computation, a very progressive forum. I will discuss why I think quantified buildings is an important wave in both architecture and science. Quantified buildings initially referred to sensor-based measurements of physical attributes like air quality, light, humidity, energy management, and so on. Here, I'm more interested in quantifying what occupants do. For me, the big future of quantified buildings lies in measuring the attributes of people in buildings, especially their behavior and ultimately their feelings. Let's start with a shocking fact. More than 85% of our life is spent in the built environment, and yet what we do in buildings is barely studied in modern science. In my opinion, it's fair to say we know more about bonobo mating behavior than about human activities in buildings. In ethology, animals are studied in their natural environment. For humans, the built environment is our natural environment. So we need to study our patterns of behavior in it. What we do where? When? For how long? Why? How do we characterize the context in which we do things? Suppose it's a building, an interior somewhere. How are we going to characterize that particular building context, that particular structural array of things, the attributes, the colors, the texture? What do we count as the situations in which we act in buildings? And then what do we do there? And of course, it depends who we are, what our roles are, what our tasks are. Very hard to study patterns of human activity in buildings without creating all sorts of scientific theories. So it's not so easy to find the activity patterns of humans as it is of small mammals. We can press the analogy of sort of ethology a little further. In evolutionary biology, there's a distinction between habitat and niche. A habitat is the spatial distribution of resources and structure. Here is a beach habitat. And one habitat can support many niches. The niche is defined as the kind of interactive, the resources and elements in a habitat that a species requires to survive, and that's where the pressures of evolution come to it in its niche. And it's a very dynamic notion. It's not easy to define or specify, but it's a dynamic one. Now we could look at habitats. We could look at habitats as akin to zones in buildings, or rather, let's think of zones in buildings as like habitats. And then since people have different roles in a given zone, then the niche is sort of like what how a role plays out and what the role feeds on and requires in that zone. And so a given zone can have many niches. each defined by the role. And a given person could have many roles, a given occupant. So to look at this airport, it's pretty clear what the functional role of this area is. But there are, of course, food courts, transfer zones, gates, check-in areas, waiting areas. These are all zones that have been architecturally designed with a few roles in mind. And that's how we would sort of imagine its adequacy. Let's look at a role in a zone more carefully. In this part of the beautiful San Lorenzo market in Florence, we have a large food court. It's a zone. It's obvious that people have different roles here. In addition to customers, some are attendants behind the food counters in the back there. Some are wait staff, and some are busing staff. You might have to stay a while to notice that when people leave soon afterward, someone comes to the table not to sit down or bring food, but to clear up. Those people have a certain activity pattern. If customers leave a table, those people, the bussers, collect used plates. They move it to trash areas or busing stations. Then they cycle around, either cleaning surfaces, tables, or reordering chairs and tables. Customers sit down, busing staff do not. Customers bring plates or are waited on, busing staff remove plates. A machine learning that observed video of occupant motion would soon distinguish those who are present for long periods from those who are more transient. Both groups, the bussers and the clients, customers, they both touch tables, chairs, and plates, but the way they touch them, who they are with, when they touch them, are different. It's a learnable difference. With luck, there are regularities in the conditions and actions that make up each group's activity patterns. So here we see again in Lorenzo Market, there's the zone would be the seating area plus the lighting and the food collection area is part of it. We've got these different roles, and we're going to characterize activity patterns by the context in which a particular action arises. And there's going to be lots of those that go into a role. So a typical rule for a diner or a stage in the dining process is to find a table. So you look around, then you walk or you look, and those are going to be the actions, the rules. The busboy has, or bus girl has a different job. We gather big data once we distribute sensors throughout buildings, especially cameras of different sorts. So what we get is machine learning, the possibility of machine learning on terabytes of data. And these are going to help us identify otherwise invisible activity patterns and the architectural context in which they're arising. What does two-person sitting activity look like? How does sitting change with architectural context? By looking and finding similar activity patterns in different zones, we can begin to identify what's common across the zones that give rise to those role executions and identify the architectural elements that contribute or support these specific roles and social activities. This view that we can quantify and look at things has obvious precursors. Paco Underhill, very much influenced by Holly White, went on in the early 90s to study retailing, and he brought in anthropologists. He set out to make a science of retail shopping. He set up cameras at the front of department stores and throughout. He wanted to know what people actually do in the built environment, in this case, in the stores. The empirical methodology he used was based on video and interview. And it was one of the major employment opportunities for anthropology students at the time. Their job was to code the videos, interview occupants, and develop simple but useful theories by classifying shopper types and identifying patterns and regularities. How do women shoppers differ from men? children, and the elderly. Are there different types of women shoppers? Clearly. Underhill found a number of regularities in shopper behavior that were directly relevant to store design. For instance, he found that American shoppers keep to the right side of concourses or sidewalks. He found that when you go into a store, you need time to slow down from the outside, walking to the store, coming in. You're not ready to really attend to the immediate stuff in the vestibule or the entrance, which said that you shouldn't put flyers or the hand baskets right there at the very beginning. They should be inside a little bit. That was the decompression zone as a result of the downshift period. He found, like others, that customers like to handle merchandise. As a result, retailers started putting out big tables with sweaters on them and other items so that people could fondle and feel them. And then, of course, everybody's favorite, the butt brush. He discovered that women brushed on the behind move away from a display. The upshot is that in the tables for touching sweaters and stuff, there's more room around those in the women's section than there is in the men's section. By adding more sensors and new sensors, we can go far beyond what Underhill could do. We can ask more questions and be more precise. We can quantify where exactly activity happens. How far apart are people when speaking, walking? You could code those in principle, but it'd be extremely difficult using video alone. If they have, if they're quantified themselves or they have a smartwatch, we could observe their heart rate or heart rate variability if we have access to it. But now there are cameras that can detect heart rate and even heart rate variability on the basis of very rapid changes in the blood flow on the cheeks, which are visible. We can see how long social interactions occur in different parts of the venue or by time of day. When do people laugh together? When and how long do they speak at a meal? And things of that sort. All of those can become parameters used to qualify activity patterns. Here's a simple quantified building setup. It's from 2012. There's an older adult over here, and there's a sensor for the door. There's a sensor, motion sensor to see when he's in the kitchen. He moves along here. There's a sensor by the toilet. It could also be on a microphone, a sensor to see if he's standing or falling in the bathtub. Over here, there's a vibration sensor to see if there's a fall or if someone's in this area. There's a pressure sensor to know, to determine properties of his sleep. And again, there's a motion sensor by the bed. That's all simple. And the macro behavior would be his walking along or standing here without knowing exactly that he's working at the washing dishes. That's slightly more micro behavior, but we would like to get even finer still. To draw this distinction between macro and micro behaviors, so the macro behaviors are activities like walking or sitting, sleeping, washing oneself, certain kitchen activities, and it would be pretty easy to detect these from coarse sensors without using video. Micro activities are components or steps in those bigger activities. And those are a little harder to track with coarse sensors. But with increased resolution, and certainly with machine learning over increased resolution, we can detect many micro activities. From motion IR, we can infer trajectory semantics and motion patterns. Here, we can tell whether someone is walking or skipping, even if they move across at approximately the same speed. We can tell because of the way the head bobs up when you walk and when you skip. So we can easily identify different kinds of gait on the basis of these things. And those could be all machine learned as they currently are.
Here we see an animation showing ID and XYZ in motion. We see very well how we can extract positions, velocities, and accelerations, and height changes will later determine whether.
So this is work that Christer Jens did, partly his analysis when he was here at UCSD. It's an analysis of people moving through a university.
We can further analyze distances between occupants while moving here from the example.
And what he found was that by having a video camera in several places, but in particular in this case one, with just one point of observation on the top of the head, you could determine position, velocity, acceleration, and various things. And over here, you could determine the distance between people. So you could tell whether people were in groups of 2 or 4, and this is all sped up. So you could then chart whether something was a person walking by themselves because they didn't spend much time very close to others. It's very simple things to talk about, but it's the start. You could even tell if someone is restless, even working at a computer at times, just on the basis of the small movements that they make and whether they're sitting or standing. And that's just the start. Because I'll go on in a second to say how things have changed, but it's a start because we have much better ways now of determining activity patterns, since the law has allowed us now to take more than one point. But before that, on-body sensors were used to study people in their natural environments, particularly people with mobility issues such as stroke or Parkinson's, or people who are prone to fall. And the trouble with this population is that their clinical assessments are standardized for one time every several months. It could even be a half a year. And during the assessment, it's a very clinical setting. So it doesn't incorporate environmental or cognitive challenges typical of their own environment. For instance, most older adults, one of the chief causes of older adult falls is shoes that they leave beside the door. Now that's part of their environment, but no one checks that. And it's a significant factor. So we would get inaccurate evaluations of the likelihood of a fall, or we would get inaccurate characterization of the mean behavior, the mean performance of a person, unless we see how it fluctuates over time. The solution was to have a wearable, but now we can begin to put these into sensors in the building. New sensors, this is a Microsoft emotion recognition application, allow one to make a good estimate of the kind of emotional state one is in. Again, that's based on video. The next step, as I was saying, is more sophisticated action analysis. And here, what we find are that using hundreds of cameras in real buildings, we can anonymize data. Because of many points, we can extract out stick figures, and we can use that to then track and count and potentially understand the actions that people are performing. We can see that Charlie here takes off his cap a little bit, and we can see he approaches her, they're chatting. There's coordination and rhythmic relations between when she claps and what he does. So all of these become elements for machine learning. There are two methods that you might use. You could either use ethnographic methods to identify and classify an action, that would be labeling it, like Paco Underhill did, but in this case, it's the action. And you could use humans to also identify architectural contexts, and then you try to machine learn the stick figure movements that correspond to the labels and generalize. So that would be supervised learning. Then you could count the actions in various contexts. In unsupervised machine learning approaches, you discover the action patterns without labels. So that's wire together, fire together, or fire together, wire together. Regular recurrent patterns tend to become things that are generalized, and then those become opportunities for classification, machine classification. Once you've got this quantified building analysis through machine learning, the next step And the exciting step is to test it using 3D game engines. So in this video lent to me by Patrick Schumacher, what we find are AI agents being used in this space to simulate how humans would find their way, building occupants, to the different sorts of seating arrangements. Now, you of course have to ask, what is driving those AI agents? Are they very simple rules like in Boyd's, where they're just a few rules that when executed in groups lead to emergent regularities? Or are they more detailed and they're related to human roles? So if we have roles, we could collect condition action rules from machine learning that in situations like this typically happens, or we could say it happens. Then we implement those rules in the AI agents. And the exciting thing is we could simulate and run this game thousands of times and count the behaviors and the interactions. And we could classify emergent behaviors, things that we're discovering right here in the game. And then these become factors that are used for better design. So clearly we'd like to know high frequency, low frequency, and the nature of social interactions. We would like to see how self-organization takes place. So if we change architectural configurations and we run our agents, then we can see what sort of social interactions and groupings emerge. Which of those are stable? We could look for the social affordances. So this surface over here is a social affordance because it keeps people at a certain distance, but yet it is an opportunity not only to talk, so they're proxemic consequences, but also they have social affordances in the sense that we could share things. And over here, there's a power relation. Someone came inside here, so now he's got a special spot. And of course, this is socially affording sitting. So we could count how fast people settle in different kinds of places, how many different configurations they find, and whether a small change in something has an outsized effect on behavior or outcomes. I would prefer to use real humans in here and use it like crowdsourcing. So using game engines with the full building design imported through BIM, then we have humans paying them $5 an hour through crowdsourcing. We give them an avatar that they can choose an avatar, but we give them a role. And then they act in the building by controlling their avatar according to their role, or we give them a task, or we give them activities. And now we have 20 of them, $5 an hour. We can have 50 people for 20 people for $100 for an hour, playing out repeatedly certain social interactions. And if we want to, we can add some AI agents to make it more populated. Eventually, AI will reach smarter AI agents. Those will have stochastic rules rather than dedicated condition action rules without non-stochastic, deterministic ones. So people act in certain ways in certain circumstances, but with a given probability, not necessarily. People usually visit coffee machines at morning time, but not always. Then we could have heterogeneous rules. So different game agents are driven by different kinds of rules. So we get new collective interactions, not just because we have different roles, but we have more complicated rules. We could try to build rational agents who are rule governed, but they have goals and beliefs, roles and preferences, in which case we would have to define all of these. It become quite complicated. But using AI agents in realistic worlds is a new opportunity for social and cognitive science. We have real buildings in there now. There are challenges. I'll be brief. How do we decide what architectural elements to include as being potentially relevant? Do we include acoustical properties in the space? In the sim that you saw, there was no sound, but of course we would have to have first-person point of view, And we would also have to have sound, and we'd have to have sort of feelings and texture of the ambience and what it's like to move through the space. All of those are potentially very relevant. Do arches make a difference? What about informational design, signage? We could try these things out, but it gets very complicated and explosively large. And then what about relational properties? So it's one thing to say that I behave in one way when A is beside B, but what happens if A is beside B, but sometimes it's near C and sometimes it's far from C? Is that going to have an effect? Every time we introduce more relational properties, the number of architectural situations we have to consider just gets explosively larger. Another problem is that niches often overlap. So the kitchen cleanup, we saw that in the case of the San Lorenzo market, but the kitchen cleanup uses the same surfaces as cooking. Well, when we're moving plates, is that part of the preparation process or part of the cleanup process? That becomes hard for machines to distinguish. Maybe it's easy if they track an individual, but we'd have to see. Roles can overlap temporally. So, of course, the busboy doesn't normally bust from the same table that the people are consuming at, so they're not overlapping temporally, but there are other cases where they do, in the case of serving. So we need to track history and know something about the agent in order to get these right. Another problem is that activity is not just single activity that can be moved together, pushed together to see what the outcomes are of individuals following their own rules, as in Boyd's or in role playing. There's some niches are really for joint activity, and joint activity is not the same as two individuals acting alone. So dressing another is a highly interactive, coordinated process where the movements are choreographed to avoid breakdown, but it's not, I mean, it's clear that the mother has one role and the child has another, but there are times when things shift about. It's not so easy to characterize this as two people each having their own script. That's not the way it works. Or two-person saw. It's extremely tightly coupled. So there are times when we have to look things that way. And one way of understanding why this is hard, why it's hard to define parameters of an activity or an activity pattern, is that when we have many activities in a given space, they encroach on each other and they deform, much like the niches, ecological niches. When the population in one niche grows, it has consequences for the others, and the others deform, in this case, like this Voronoi diagram. As it begins, one changes, it squeezes, and the others all have to adapt. So activities co-adapt. In Starbucks, something I studied, there are many overlapping activities systems. And so if you optimize the architecture for one activity system, you are likely in a Pareto less position above diminishing the activity system, another activity system. So that becomes an extremely hard issue. The bottom line is that human environments are not animal environments. We can't study them quite the same way. We have so many roles and so many, therefore, niches and so many tasks within each role. Tasks are almost like micro niches. Activity patterns get quite task specific. So we have a lot of scientific work to do. My conclusions are that cognitive science is inevitably moving toward a more ecologically natural science. That means capturing humans in the built environment, their ecological home. Developing the appropriate analytical tools for some of the reasons I just gave will not be easy. It will certainly be based on big data. There will be privacy concerns because anonymizing small group activity of small groups doesn't really anonymize things since you can guess who the actors are. Creating the realistic AI agents, which I believe will be a major part of social sciences and cognitive science, will be a major challenge. But the outcomes for architecture, for science, are as high as our scientific and artistic imagination can run. I think we're starting the dawn of a new era. Thank you.
Thank you very much for the great presentation from Professor David Kirsh. Super interesting.